Okay, question 4 is about amino acids. First thing it asks you is for the general structure of an amino acid, and there it is. Remember the carbon in the middle with the amino group and the carboxylic acid group both attached to it, a hydrogen, and then this is the variable bit which we write as R. That's what's different between the different amino acids. Then we have to say what happens to that structure when it's dissolved in water at different pHs. Low pH, remember, means acid. Lots of H plus ions around, so it will grab as many H plus ions as it can. COOH, can't do any more, but the amino group, remember there's a lone pair on that nitrogen, which means, like any amine group, it's basic, it can pick up H plus, and that's what it will do at low pH, so you'll get NH3 plus at that position, and that's the low pH form. The isoelectric pH is the pH at which the overall charge of the amino acid is 0. And so that means that the positive and negative charges have to cancel each other out, and we get what we call a zwitterion. So what happens is that stays positively charged, this one becomes COO minus. So that's the zwitterion form, and that's the species that's maximally populated at the isoelectric point. If you're asked to define isoelectric point, you just say it's the pH at which the overall charge on the amino acid is 0. Okay, then we get on to some NMR stuff. First of all, it's prompting you to think about what happens in D2O, because in the problem that comes next, the spectra are obtained in D2O, so it's just helping you out a bit really. And what you have to remember is that if you have OH groups, and you dissolve it in D2O, that hydrogen becomes replaced by deuterium. So you get OD, and the point is that deuterium doesn't give a proton NMR signal, so the OH peak will disappear from the spectrum if you add D2O. Same with NHs. If you have NHs, they become ND, and again, they disappear from the spectrum. Okay, now we get on to the big one, which is working out the structure of the amino acid. So the point is we know that it's going to be basically that, and all we've got to figure out is what R is. So it's actually a relatively straightforward question, because you know a lot of the structure straight off when you're just working out what the extra bit is. Now when you get a question like this, what I suggest you do is try very quickly to figure it out in rough, and then write down the structure that you figured out and explain how it fits all the data. That's the easiest way to do it in terms of structuring your answer. It's harder to sort of think out loud and do all the thinking and then arrive at the conclusion at the end. But if you can't figure out what the structure is, then obviously that's what you have to do. So let's quickly see how we sort of figure out in rough what's going on, and then we'll go through and explain how it fits all the data. Easiest place to start is here. That, remember, is the molecular ion peak in the mass spectrum, the one with the biggest value of M over Z, and it gives you the MR of the compound. Okay, so from the molecular ion peak, you know that the MR of the compound is 89. And that actually is pretty much all you need to figure out what's going on. Because when we come to this molecule, this bit, the amino group and the CH and the COOH adds up to 74. So you can deduce that the R group must be the rest. In other words, that adds up to 15 to give you the overall MR of 89. And 15, of course, is the mass of the methyl group. So you can be pretty confident that what this amino acid actually is CH3 as the R group, like that. And all you then have to do is go through the rest of the data and check that that fits. So that's what we'll do now. So we've explained the molecular ion peak. It's also worth, if you have a big fragment peak in the spectrum, it's worth having a quick look and see if you can explain where that would come from. 44 is 45 less than 89, and 45 is the mass of a COOH group. So it's likely that that peak at 44 comes by breaking this bond here and losing the COOH group. In other words, that comes from this fragment, H2NCH3 plus. That would account for the peak at 44. Proton NMR, remember it's in D2O, so we're not going to see these protons or these protons because they're replaced by deuterium. So we're just going to get two peaks So that straight away fits, and say that gets you a mark. 2 types of non-equivalent protons, so 2 peaks, which is what you observe. Let's start with these 3. You should get a peak area of 3 for those ones, relative to a peak area of 1 for this one, obviously because there are 3 hydrogens contributing, and that's shown in the integration trace. Remember, if you see lines like this above your spectra or going through your spectra, that's what they are, integrations of the peak area, and if you measure it with your ruler, you can indeed see that that one is 3 times as high as this one. So the area is 3, that fits. The splitting, well, the adjacent carbon is this one, and that has 1 hydrogen attached. Remember, the n+1 rule says that it splits into 1 more than the number of hydrogens on the adjacent carbon. So adjacent carbon has 1, it should split into 2, which it does, it's a doublet. So that fits. Chemical shift, well, it's just an RCH type proton, because this carbon that the protons are attached to is just attached to another carbon, it hasn't got anything directly attached to it. So it's an RCH, which gives chemical shift between about 0.7 and 2, and that fits with this peak at about 1.4 ppm. Okay, so you can account for the shift, 1.4 ppm for an RCH proton, you can account for the splitting, you can account for the area. This hydrogen, therefore, accounts for the other peak. Why is it a quartet? It's a quartet because the adjacent carbon, which is that one, has got 3 hydrogens attached. So n+1 rule again, 3 hydrogens gives you quartet. So we can explain that. The peak area is 1 because there's only 1 hydrogen. The slight fly in the ointment is the chemical shift. Chemical shift doesn't fit, and that's because it's a bit complicated here. If you're trying to figure out what the environment of that hydrogen is, you could say, okay, well, it's an HCN type peak because we've got HC with a nitrogen attached, but it's also HCCO because you've got CO attached on that side. And both of those groups cause perturbations to the chemical shift, which you could use to make a prediction. The problem is, though, that when you have both of them, those perturbations add up, and they often cause the shift to be outside the range you expected. So you just have to detail that. You'd have to say, well, HCN means it should be between 2.3 and 3. HCCO means it should be between 2.0 and 2.9, but it's actually not within those ranges, and that's because of the effect of having both of them means you can't make a simple shift prediction. Okay, that's it for accounting for the spectrum, so that's actually not that hard a question. Okay, we're going to pause there. I'll do the remaining parts of that question in a second. You know what I mean by that in the next film. Okay, stopping here now.